And well, I begin with mirror devices. The first one is the Weber bar. It's the first one in 68 Webers to it. It consists of many cylinders of aluminium with dimensions 1 meter of diameter and 2 meters of tall at temperature approximately to 0 Kelvin. It has an antenna form. And vibrates 1660 Hz. And could detect deformations about 10 power minus 16 meters of around of 10 electrons. And the mini grail is the most important of this type, but with the particularity that it has a spherical form, and for that it's able to detect all gravitational. It's able to detect all gravitational waves independently on the polarization. Why? Because in the other in cylindrical form, only it's capable to detect the gravitational waves coincide over the basis of the cylinder, while in the spherical form, all the sphere is the basis, is the detector. And well, the characteristics are that 68 centimeters, 1,150 kilograms, that resonates at 3,250. It works at 20 millikelvin. Well, it is isolated from vibration by 140 kilograms masses. Can detect oscillations around 10 to minus 20 meters. The 100th part of an electron, or 100 times smaller than an electron. This is the mini grail. And now I explain the laser interferometers. It was discovered by many groups independently, but the time when they discovered this form, or this form to find gravitational waves, there are not a study of the noises that perturbs this device. And then Weiss in 72 did the study of these noises, the limit of this device susceptibility. And for that, nowadays we can use this type of devices. Normally, the laser interferometers consist. Well, normally no. The land laser interferometers consist in two arms perpendicularly with laser inside. In space type, the arms are spaceships, but these well, it's the same process. It's the same laser interferometer here in land or in space. The only difference is the arms. The arms or the arms. In land, there are arms, and in space are spaceships. Well, and then how work it? You have an interferometer like that. Okay. When a gravitational wave incites over this interferometer, that it is in the direction of the polarization of the gravitational wave, then the length of this arm that it's equal to this length varies when gravitational wave incides over that. What happens where gravitational wave incides over that? This contrains and this expands, and due to that there will be interferences. The laser interferometers normally are Michelson. Okay, is the typical Michelson-Morley interferometer. Advantages of this from the Weber, they are more sensitive because it's able to detect frequencies that cannot be around the resonance point. And there are two types, like I say, ground type and space type. Ground type, two perpendicular arms of many kilometers of length aligned to gravitational wave polarization. The frequency of the light, the frequency that can detect, around 10 and 1000 Hertz. But it has a lot of problems due to the ambient noises and masses that surround it. That's the noises that affect this device. The thermical, the seismical noises, whatever. One hand detects the squeezing and the other detects the stretching, that I explained before. And the variations in arms are about the radius of an electron. And now I explain the LIGO. LIGO is an interferometer, a Michelson interferometer with Fabry-Perot arms. There are two observatories, spaced 3,000 kilometers. One has 4 kilometers arms and the other 2 kilometers. This is Fabry-Perot. There are two mirrors that makes the light bounces 50 times. I will explain later this. The advantages of two observatories. Well, this we can dismiss seismic noises and instrumental errors. Why? Because if one of the observatories notes or notice seismical noise, the other will not notice this, because the distance is a noise, a local noise, and the instrumental errors is the same. Is a noise that only affects one of the observatories. It's practically impossible to have two observatories with the same problems and exactly the same noises. The power of the laser is 35 watts, and well, this is it's LIGO. This is the interferometer. We have a laser that sits on beam splitter. The beam splitter splits the laser on two ways, this one and this one, and here there are two mirrors. This mirror has totally reflects totally, and this one also, and these, the recycled mirrors, have no totally reflection. Then a photon is trapped here until he can escape over 50 times between the mirrors. Then this distance that it is 2.5 miles, thanks to these mirrors, we can well, it's like interferometer. Bigger, a bigger interferometer, because this distance, how the photons are reflected 50 times. This is like an interferometer 50 times greater. Then, well, like an interferometer. Then later the beam escapes and converges here to the photodetector. If the length, well, these lengths are equal, and when a gravitational wave incides on this detector, these lengths varies. This is shorter and this is larger, or the inverse. But this difference of longitudes, of lengths, makes possible to detect the amplitude, or to measure the amplitude of the gravitational waves. Well, other ground interferometers are these: the Virgo, that it's in Italy, the Heo 600, that it is in Germany, the Clio, that it's in Japan, Tama 300, that it's in Japan, the LCGT in Japan, and well, and now the LISA. LISA. It's a space-type interferometer that it's being developed by this and the NASA. Consists in 3 spaceships spaced 5 million kilometers in an equilateral triangular form, like this. We have the orbit of the Earth, and LISA orbits the Sun at the same distance that Earth, and it has a equilateral form, and the distance between these spaceships are 5 million kilometers, and the distance between the Sun and the orbit of LISA are 150 million kilometers. Then the sensibility is around these values, 0.00003 milliamps and 100 milliamps. That it's smaller than the sensibility of the land types, and this permits to measure gravitational waves of sources different to the land type. Like this one can measure gravitational waves of black holes, supermassive black holes. Well, LISA will observe gravitational waves by measuring differential changes in the distance between spaceships. It's plus or minus the same like the typical interferometer in land, but the difference is that in land there are arms, here there are spaceships, and well, the main goal of this interferometer and of all interferometers is to prove that the Einstein's general relativity and the study of astrophysical systems are not resolved. And well, this is all. This is the bibliography I used, and well,